Hello everyone, my name is Marco Piacentini and I work as a PhD candidate at NTNU in Trondheim, Norway. My co-authors are my supervisors, Chao, Chiara Bertolin and Bjørn Skallerud, and the external collaborator Filippo Berto from Sapienza University. Today, I will speak about the first steps that we took towards building a deep learning framework for the prediction of nonlinear property and failure in trabecular structures. Before getting into the work itself, let me give you a bit of context and motivation. I'm part of the GAP project, a Marie Curie action focused on deepening our understanding of structural property relationship in trabecular bone, which is the material that you can see here on the screen. We are particularly interested in fracture mechanics and understanding how crack nucleation and propagation depend on microscale morphology. Using micro-CT, we can capture in 3D how fracture interact with the local morphological features with micrometric resolution. However, acquiring and processing such high-resolution data is complex, and on top of that, bone has a highly nonlinear material behavior and hierarchical structure with many complexity all occurring at the same time. So the goal of this work is to start building a predictive framework that simplifies these complexities using artificial structures that resemble the trabecular bone but are easier to control. We begin by focusing on the first hierarchical level, the trabecular network itself, and by using synthetic structures, we can temporarily avoid the complication of image acquisition, post-processing, and heterogeneous material properties. Among the common artificial representation of trabecular bones, two families stand out: sphenoids and Voronoi tessellations. In this study, we focus on Voronoi structures because they allow us to tune both global and local geometric features. Many methods exist to smoothly control their aspect ratio, orientation, and cell density. Furthermore, several post-processing strategies can also morph them from open to closed cell or from rod to plate-like morphologies. Now, to give you an overview of this talk, I'll first describe the material and method used for structure generation, finite element analysis, post-processing, and deep learning training. Then I'll move on to the results and conclude with our main findings and future directions. For this preliminary study, we use anisotropic disordered 2D beam networks generated via periodic Voronoi tessellation. The idea was to start as simple as possible and progressively increase complexity later. Periodicity simplifies boundary conditions, while beam models drastically reduce computational costs. Anisotropy was introduced by deforming an initially isotropic Voronoi tessellation, first compressing it to create a preferred orientation, then rotating it to change its direction. However, rotation normally breaks periodicity, so we generated the tessellation inside a predeformed domain that restores periodicity after deformation, producing a square representative volume element with the desired anisotropic geometry. We impose periodicity following a common approach by generating a tessellation on a 3x3 repeated tiling of the same random seed distribution. This distribution, as previously said, was counter-deform, used to grow isotropic tessellation on this deformed domain and then deform back into the final anisotropic configuration. The central tile is extracted, and this is our representative volume element, and this is only the central tile is where we get the suitable boundary condition for the periodicity. This strategy works well for 2D solid models, but since we used beam models, we needed to eliminate very short edges that violate beam assumptions. To do so, we merged nearby nodes using a KD3-based algorithm. However, this occurs with some limitation in terms of the achievable volume fractions and also on the trabecular morphology that are obtainable. The design space of our dataset was defined by three parameters: aspect ratio from the compression, orientation angle from the rotation, and the number of nucleation points or seeds. You can see how these parameters influence anisotropy in the examples here shown. And you can also see that the aspect ratio range from 1 to 3, the orientation from vertical 0 degrees to horizontal 90 degrees, and the number of seeds from 10 to 50. In total, we generated 10,000 structure uniformly distributed across this design space. At the bottom of this slide, you can see 4 representative samples from the actual dataset. While instead on the top, you can see a scatter plot of the resulting volume fractions versus the generation parameter. We are interested into the volume fractions as these are key descriptor of the mechanical properties, as mechanical properties scale at least linearly with decreasing volume fraction, and it is known as the Gibson-Ashby upper bound. As expected, the volume fraction correlates strongly with the number of seeds and also a little bit with the aspect ratio. Finite element analysis were carried out in Abacus standard using general static. Each strat was modeled using a quadratic Timoshenko mean with 4 elements, enough to capture the deformation that we were interested in for this study. And the Timoshenko formulation relaxes also the slenderness constraint, making it suitable for moderately thick beams. Periodic boundary conditions were enforced on both displacement and rotation using constraint equations. And we then applied uniaxial compression, limiting iterations to 100 maximum and using a minimum increment of 10 to the minus 6. Both beam thickness and RV size were fixed, respectively at 0.22 millimeters and 75 millimeters. These are out of the physiological bone ranges, but these are due to the limitation of the beam modeling. And yeah, we are gonna target physiological ranges in the future with more complex structures. Also for the material, instead of using bone, we focused on a testable material, a resin model with a bilinear elastoplastic isotropic hardening. After the simulation, we post-processed the global responses to extract effective properties, treating each structure as a fictitious homogeneous material. We computed the Cauchy stresses and logarithmic strain, derived the instantaneous stiffness, and from this we derived the yield strength using the 0.2 offset method, which is also illustrated in this slide. Ultimate tensile strength was identified as the first stress peak when present, but since this was not always well defined and it's not a rigorous definition, it was excluded from the deep learning stage. The extracted properties were then analyzed in relation to generation parameters, as we will see next. The deep learning pipeline used a simple, yet often effective architecture, the multilayer perceptron. Multilayer perceptrons have been previously used to predict stiffness from parametric representation of various microstructures, including 2D Voronoi networks, although with a fixed number of generation seeds. Briefly, multilayer perceptrons consist of fully connected layers of neurons, where each connection carries a weight, and the overall passage from one layer to the other can be modeled as a matrix multiplication. This matrix multiplication is also followed by a nonlinear activation function to introduce expressivity and avoid the collapse to a single matrix multiplication throughout the model. We used ReLU as activation function, and we tested 3 models in total, each predicting stiffness and strength. The first model used only the 3 generation parameters as an input, while the second used only the explicit node coordinates of the sorted nodes. The third model instead combined both input, so both the generation parameters and the explicit node coordinates. However, it has to be pointed out that network such as MLP cannot naturally process this kind of data, especially for structure with such a variable size. And networks such as graph neural networks can instead be more suitable for this purpose, but those are left for future work. All models were trained in MATLAB with the Adam optimizer and using a mean square error loss. The training parameters were set equally for all the models, as you can see here in the table. Now, to the results. Here you can see the process Cauchy stress logarithmic strain curves color-coded by generation parameters. You might already be able to spot some trend, but they will become clearer in the next slide. Here you can see the scatter plot of the extracted yield points, both in linear and normalized log scale for ease of visualization. Structure with the highest stiffness and strength correspond to those with many seeds, high aspect ratio, and vertical orientation. So this combination is coded with a yellow color. Reducing the number of seeds lowers both the stiffness and strength, while rotating high aspect ratio structure towards the horizontal increase yield strain but decreases the strength and the stiffness. And we can also observe the trends for the extracted ultimate tensile strength, and we can see that they are substantially analogous. Furthermore, we observe that the scatter of each property in relation to the generation parameters of the corresponding structure confirm what we had already observed. The number of seeds, due to its influence on the volume fracture, is the primary determinator for the mechanical properties, while another dramatic effect is given by the orientation in presence of high aspect ratio, where orientation aligned with the axis of compression increase stiffness and strength as expected. Normalizing the results by the Gibson-Ashby upper bound for stretching dominated materials shows that all values are well below 1, meaning our structures behave as bending dominated and follow a superlinear scaling with density. The overall trends remain consistent to what presented before. So also the deep learning results align with the expectation. The simplest model, based only on the global parameters, perform reasonably well in both training and testing, but cannot reach very high accuracy. And this is not surprising, as it lacks the information to distinguish similar structures with different response. However, as you might notice, the model that includes such a level of local detail through the local coordinates actually perform worse. And this happens because multilayer perceptron are ill-suited for handling graph-like data, especially with such a variable number of nodes. So the second model, which used only the coordinates, performed the poorest, as we said, the multilayer perceptron is not able to handle correctly this kind of data. Instead, the model that had both the generation parameter and the local coordinates is able to somewhat recover the performance of the first model, but overfit on the training data due also to the higher complexity of the model, which is given by the higher number of neurons, and performs worse in the testing dataset. So to summarize, the results tell us that current global parameters are unsuitable for achieving accurate prediction because we are not able to sufficiently discriminate similar but different structures. And crucially, in general, we have seen that multi-layer perceptron are poorly suited for handling graph structured data that will enable us to distinguish these structures. Overall, these findings suggest that future work should move toward architectures designed for structured data, such as graph neural networks, which can better exploit local topology and also be used to predict special fields like stress or fracture path. In parallel, we plan to overcome current limitation by moving from beams to solid models, first in 2D and eventually in 3D, progressively increasing realism and complexity of the structure that we're going to tackle. With that, I conclude my presentation and thank you all for your attention.